Okay, so uh, this is a special class for MYP chemistry. This is MYP4, right? So I have a list of questions that I'll ask you. These are all concept-based questions that you should be able to answer. And we will primarily focus on chapter 3, 4, and 5 from the book. All right, so first question. This is about the chemical bonding that substances have. So how do you tell what kind of bonding anything has? Sorry. Now, for that, the usual parameter is, and if you remember from the class when we did the practical experiment, was that we look at, is the thing soft or hard? Does it have high melting and boiling point? Similarly, does it conduct electricity as solid? And then does it conduct electricity as a liquid? Okay. Thirdly, we look at things if they dissolve to conduct electricity, like they don't conduct as a liquid, but they dissolve. So they conduct as solution. Okay, so these are three different ways we look at things when they conduct electricity. Most of the time, things that dissolve and things that are liquid, they usually behave in a similar fashion. So let's look at this. If we want to check if something is ionic, then remember, ionic compounds, they have a strong lattice, right? And in that lattice, you have ions. Those ions are charged, so they can conduct electricity if they are able to flow. And in ions, in ionic compound, in the lattice, they're fixed. They can't flow. So it does not conduct as a solid. But if you melt it, the lattice goes away. So yeah, they're free to go and they will conduct. Similarly, is it hard or soft? It is hard. Because again, the lattice is strong. It's holding them all together. So they're like that. And as long as you have a lattice, it's going to have high melting point. Okay, so ionic compounds, they don't conduct as a solid, but they do as a liquid. But they're hard, they have high melting point. Clear? Okay. Now, how about things that are molecular? Molecular means like water or acids or that kind of thing. Ebook, I have uploaded the ebook on Manjack, so you can just check it from there. So molecular substances, are they soft or hard? They don't have a lattice, right? That's the main criteria there. They don't have a lattice. And when they don't have a lattice, that means they are loosely bonded. They're soft. They can easily break. Some of them are hard actually because they are brittle. So they won't ask you specifically about this. But in general, if you make a solid out of them, they'll be hard. But because they are loosely bonded, they have weak forces of attraction between the molecules, they have low melting point. Okay. So understand the difference here? Molecular substances, they're usually liquids or gases at room temperature. So the idea that, oh, is it soft or hard doesn't really count because it's a liquid. So liquids can't be soft or hard. Like water is soft or hard, but that's in a different sense of the word. Similarly, do they conduct? No. Do they conduct as liquid? No. But some of them conduct when you dissolve them in water, and that is for acids. So while acids are molecular, they will conduct only when you dissolve them in water. As a solid, as a liquid, they can't. So, and that's true for most molecular compounds. So water is also an example of this. Water is molecular. It has a low melting point, doesn't conduct as a solid, doesn't conduct as a liquid. But the moment you mix it with something, you make a solution, it starts to conduct, it forms ions. Okay. So acids and water and even alkalis do that. Okay. Ammonia, for example. Okay. Moving on. How do you know if something has a giant structure? So again, giant structure means it has strong forces of attraction. Just like ionic compounds, it has a lattice. So it is hard. It has a high melting point. Does it conduct? No. As a liquid, we don't talk about it because it's giant structure. They have very high melting point. We don't really melt it or we don't achieve that temperature. But yeah, even if it did, it will not. But there's an exception here. That is graphite. Okay. So most giant substances. Can you think of any giant substance?
diamond.
Hmm?
So diamond.
Guys, wake up. Can you think of any giant substance?
Sir, आवाज आ रही है? Hello.
Shahnaz, I can't hear you. Can you say that again?
Diamonds.
Yeah. Silicon dioxide. Yes. That's like that. Diamond is like that. But graphite is different because graphite, even though it's giant, it has a high melting point, but it's soft. And it conducts as a solid. And the reason for that is unique to graphite. The reason that graphite has is actually the same reason that metals have. So I'm going to move all of this to this left. So if you look at metals, then they behave in a similar fashion as graphite. Are they soft or hard? They're soft. Do they have high melting point? Yes. Do they conduct as solid? Yes. So you can clearly see that graphite is acting like metals. So even though it's a giant structure. So what's the reason? Metals have layers, graphite has layers. Metals have strong force of attraction, graphite has strong force of attraction. Metals have free electrons, graphite has free electrons. Clear? So just to recap, how do you tell if something is ionic? It will have high melting point, it will be hard, and it won't conduct as solid, but will if you melt it or add it to a solution, like sodium chloride. How do you know if something is molecular? Doesn't conduct as solid or liquid, has low melting point. How do you know if something is giant covalent? It has high melting point, it is hard, but doesn't conduct in any state. How do you know if something is metallic? It conducts as a solid, high melting point, high density, and it's soft. So you can make sheets out of it, you can make layers out of it, all of that malleability discussion that we had. Okay. And of course, there's few exceptions, like in giant, you have graphite, which acts like metal. So all of its properties are similar to metal's properties. Okay. All right. So that's the first thing that I wanted to talk to you about. So let's say there's a solid at room temperature, which only conducts electricity if you dissolve it in water. What kind of structure does it have?
A lattice.
Maida, can you say that again?
Won't it have like a hard structure like a lattice and then when it's dissolved in water? Oh, let me type it down.
Give me a minute. Can you say that again? Okay, so you're right that it might have a lattice, but again, the question is, what kind of bonding does it have? So lattice exists in all kinds of bonding except molecular. So my question is that there's a solid that conducts electricity only when dissolved in water, doesn't conduct as solid, doesn't conduct when you melt it. What kind of structure does it have? Molecular. Yeah, that's correct. That's correct. Okay, another question. We have discovered a new substance and it is really soft. You can make sheets out of it. It conducts as a solid and it has a very high density. What kind of substance is that? Yes, Mahada, you're right. It's a metal. It might not be graphite because we just said that we have discovered a new substance. So graphite isn't really a new substance. We already know about it. Okay, here's another question. We have discovered a metal that conducts as a liquid, conducts as a solid, is very strong, but it has a low density. What use can we put this thing to? It's a low density metal. It's strong, but low density. Where could we use it? It does. It's a metal. Yeah, it does conduct as a solid or liquid. Why are you typing? Why don't you unmute yourselves?
Sir, can you hear me?
Yeah, I can hear you.
Oh,
So what do you think? Where could we use this thing?
so can you repeat the question?
It's a metal that's strong. It conducts as a solid and it has low density. What is a useful thing we can application of this thing? Yeah, it does act like aluminum. Yeah, sounds like aluminum. Aluminum has high density, low density, and it's really strong. So where do we use aluminum?
Sir, aeroplanes.
Yes, aircraft parts. Yes, very good. Very good. And that's because it has a low density. Okay. So that's the kind of questions or concepts you need to know for metals or the other bonds that you have. Okay. Next question is, how do you determine the state of anything at room temperature? How do you know what state something has? If I tell you the melting and boiling point. So let's say I have three things. There's A, B, C, and the melting points are given. So, and boiling points are given. So it's like 108 and 254, and this is minus 37 and 23 and 40 and 92. So this is what I have. Okay. So I want to figure out the state of this thing, A, at room temperature. So how should I do it? How do you know what state A is at room temperature? Okay, before we do that, do you know what
Sir,
the temperature
solid?
is at room temperature? So what is the room temperature? What's the value? We take the room temperature to be 25. Okay, so room temperature is taken to be 25. So here's what I would suggest we do. One simple technique that I use it, that I basically write the states like this. So solid, liquid, gas. Basically, when the temperature is less than their melting point, when the temperature is less than that, it's going to be a solid. When the temperature is more than the boiling point, it's going to be a gas. But between these two, it is going to be liquid. And next thing I'll do is I'll put 25 as if this was a number line. So is 25, where would 25 come? Here, here, or here? So 25 is less than 108, right? So I'll put 25 here. Here, the 25 is going to be here because it's greater than 23. And here again, the 25 is going to be here. Because you see 25. 25 is the room temperature. We always take it to be 25.
So that's like fixed temperature for room temperature.
Yeah, it's a standard temperature that we have for room temperature. It's always 25 degrees Celsius. So what this means is that this thing is a solid at room temperature. This thing is a gas at room temperature. And this thing is again a solid at room temperature. So that's a very convenient way we can identify the states. So for example, if they say, okay, if not room temperature, what is the state of this particular thing, each of these at 100 degrees Celsius? So again, you'll put 100 there. So for example, in this case, 100 is over here. In this case, 100 is over here. And in this case, 100 is over here as well. So we'll say this is a solid at 100. These two are gases at 100. Okay. So no matter what temperature they give you, as long as you know the melting and boiling point, you can identify the states. Any questions? Do you understand how to solve this? So for example, if I gave you a new substance, D, and I ask you, okay, the temperatures are like, now what will its state be at room temperature?
Liquid.
Very good. It is
A
a liquid.
gas.
It will be a liquid because you see, 25 is over here between -35 and 332. Right? So it will be liquid. It will be a gas at temperature more than 332 on this side. Does that
Room
make sense?
temperature.
Yeah, room temperature is over here, yes. Okay. Next question. When you have metals, how do you differentiate between different metals? Like, how do you know which one is a group 1 metal and which one is a transition metal? Okay. So one way of looking at that is that, let's look at metals again. We talked about metals and we said that they are soft, they have high melting point, and they conduct as a solid. And all metals do that. All metals do that.
Sorry?
But yeah,
Don't you identify the difference of metals based on their number of electrons?
so again, there are transition metals that will give you 1 electron for each atom, and all the group 1 also gives you 1 electron for each atom. So that's not really a very large difference. Secondly, we can't really count electrons, can we? Just by looking at the things and all. So we need a more easy to understand parameter, something that we can easily check. So one thing that we do for group 1 is that group 1 metals are really soft, which means that you can cut them with a knife or you can cut them with a caie. And if you remember in the class, we did that. We use a ruler, the plastic ruler, to cut sodium. We can't do that with the transition metals. Similarly, group 1, they have low melting point. And most importantly, group 1 metals float on water. Remember sodium, it was shooting across the surface. So they have such a less density that they float on water. But the other metals don't. The other metals are, they are high density. Okay. So for group 1, we can see that group 1 metals are soft. They have low density. They float on water. Okay. And they have low melting point. And that's usually the case. Of course, lithium is slightly different, but we don't study lithium as much. And remember, if there's any exceptions and all, like to this basic concept, then the examiner will tell you about that exception. Now, transition metals go a little beyond that, and they're much easier to identify. Because transition metals are just like regular metals, so they have high density. So it contrasts with group 1. They have high melting point, which is again is something that's different from group 1. Okay. Then they're much malleable, but group 1 is also malleable. But it goes a little beyond that. So transition metals, they have colorful compounds. So any salt of transition metals will be colorful, especially if you add water to it. Group 1 will not. Like you take sodium chloride, you add water to it, it will either dissolve or just stay white. But transition metal like copper sulfate, which is white, you add water and becomes blue. If you remember, we did that in class. Similarly, one important concept that transition metals do, and that always gives them away that, oh, this one is definitely a transition metal, is that they will make different compounds with same element. So let's take an example of, let's say, oxygen. So if I react oxygen with iron, then I can get iron 2 oxide, and I can also get iron 3 oxide. And again, I'll talk about how we get these formulas, but you can clearly see that even though this thing is also made of iron and oxygen, and this thing is also made of iron and oxygen, there are 2 of these. Now, that's not the case with the other metals. Like with sodium, you can always get sodium oxide and there's only one formula for that. But with this case, you have 2 different compounds. They have completely different properties. For example, let's take, I don't know, let's take fluorine. So copper, when it forms bond with fluorine, it can form CuF, or it can also form CuF2. So again, because copper has different variable oxidation states, or in other words, the charges on these things are different. Like over here, iron is +2, and over here, iron is +3. Similarly, over here, copper is +1, and over here, copper is +2. So because of these variable charges, variable oxidation states, they form different compounds. And this is also the reason why they have colorful compounds. Different colors come because they have different variable oxidation states. And that thing is unique to transition metal. So if somebody says that, okay, this is a metal, but it forms multiple compounds with nitrogen, that is a dead giveaway that this is a transition metal. There's absolutely no other way. So where do we use them? That's also a question that can be asked. That where do we use transition metals? Go on. Can you identify a use of transition metal? We know that they have high density. They have high melting point. So we can use them in construction material. Transition metals, where do we use them? Similarly, they are
for industry purpose.
what industry?
Um,
So we have to be a little specific. So for example, they conduct electricity, right? So we can make wires from them.
transition metal.
Yeah. So we make copper wires. And it's not just that they conduct electricity. We also use them to conduct electricity because they are malleable. They are ductile. You can make wires from them. They're very flexible. So you can make wires from them. Okay. And now here's the question. If we make wires from copper, can we make wires from silver? So again, you have to look at, does silver behave in the same fashion as copper? Is silver malleable? It is.
I think
Go on, Tayyip.
no, sir. Okay.
So silver is malleable. Silver does conduct electricity. So does copper. So you can do it. You can do it with gold. You can do it with iron. So because the transition metals have similar properties, you can use them for similar functions. Okay. Hamda, malleable means that you can make sheets from that thing. It has layers and you can make sheets from those layers. That's what malleable means. Okay. Next question is that I want to talk about is how do you make formulas? Okay. So how do you make formulas? For that, you have to first understand what kind of bonding something has. So for example, if something has like an ionic compound, let's talk about that. If something is ionic, then it will have a cation and anion. Okay. So let's take the example of, let's say, iron 3 oxide. Let's do that. So iron 3 oxide. So first step, you have to write the ions. So iron, what does this 3 mean?
So bracket size.
That has like 3 ions in its like outer ring shell, like 3 electrons in its outer ring shell.
Yes, exactly. So it has what? 3 as the charge. So it's not that it has 3 in the last shell. It basically means that it has lost 3 electrons. Okay. Get it?
Yeah.
Great. So we write +3 here because that's the charge that this thing has. Similarly, for oxide, what's the charge? We'll have to go to the, what you call it?
-3.
So we'll have to go to the periodic table for that.
So it's going to be -2.
-2, exactly, because it's in group 6. So that's what it's going to be. And after that, we do this. What? Learn from Akshay, okay? So you basically take the charges and you flip them. Okay? So this goes here, this goes here. So it becomes iron 2, iron with 2 and O with 3. That's a positive, not an F. That's a positive, Alicia. Okay?
Are they going to give the charges like 3 plus and 2 minus in the exam?
So they will give you the periodic table. So you have to figure it out from the periodic table. But for transition metals, you can obviously figure them out from the name. Now, remember one thing. The final formula that you have, it will not have a charge. Because the whole point of making a compound in this way is to get rid of any charges because compounds are neutral.
A charge of 2.
What do you mean a charge of 2?
Sir, how do you figure out the charge for the periodic table?
Okay, so the group number tells you. So group 1 means that it has 1 in the last shell, so it's going to lose that. Because remember, they are going to go for 0 or 8. Okay, that's the octet rule. That they either try to get to 0 or they try to get to 8. Now, group 1 wants to get to 0. So if this was 0, this was 8. Group 1 is over here, so it will try to go to 0. And that means it loses 1 electron. It's +1. Group 2 will try to go to 0 again. Group 3, again, +3 because it loses 3. Group 7 goes to 8. For that, it has to gain electron. So -1. Group 6, -2. Group 5, -3. Now, group 4 is interesting because group 4 can go either way, here or here. So usually what group 4 does is that it goes for +4, +2, or very rare cases, -4. So just to sum it up, +1, +2, +3, -3, -2, -1, and the group 4 is in the middle. Now 8 will never go anywhere. So that's why the noble gases don't react at all, because they don't need to gain any electrons or lose any electrons, right? So that's why sometimes we also call it group 0. Clear? Yeah, great. Now, what if you had something with similar charges? So let's take the example of iron with +2 and oxide with -2. What do we do in this case? Do we write 2 and 2 or do we just cancel them out?
Sure, we'll cancel them out.
We cancel them out, yeah. Because remember, the point is to make sure that you have a simplest ratio. So this will be FeO because the charges cancel out. Now imagine if I had this thing. Now what will I do?
Sure, it would be PbO2.
Very good. So basically, it's not the charges, it's the ratio that flips. So ratio flip, that's what happens. So the ratio of these charges, that's what you have to cancel out. So when this cancels out, gives you 2 and 1. So the 2 goes here and 1 goes here. Okay, so that's how you write the charges. Now, if I already gave you the formula, so I'm going to tell you a compound. How about you make the formula? So aluminum nitride. Go on. Use the periodic table. You can open it on your laptops and try to figure out the formula. Go on.
So they both have the charge of 3. So aluminum have 3 positive and nitride have 3
Excellent.
negative.
Yeah, that is
So it
correct.
would be
Aluminum is plus
Al.
3.
Yeah.
Okay. Tayyib, can you explain how do you got -3 here? So the idea is that because nitrogen is group 5, it will
So
gain 3
basically
electrons.
the optic from the optic one.
Yes.
I got.
Yes. Good. Okay, I'm going to give you one more. Try to figure this out. Copper 1 oxide. Go on, do it.
So what is meant by the bracket no 1?
That means copper has a +1 charge.
Will there be like 2 copper atoms?
Yeah. Ions actually, not just atoms.
Okay.
So copper is +1, oxide is -2. So the cross multiply and you get Cu2O.
Sir,
Okay.
I got,
Yeah.
but I still didn't get the periodic table.
What do you mean?
Like, I don't know how to find out the charges with the periodic table.
Okay, so in the periodic table, just look at the group that you have. So group is always the column that the thing has. So group 1 needs to get to 0. So it all has to come from the group number that you have. So for example, in this case, aluminum is in group 3. That means it will
We're
try to
going
go to 0.
add the transition metal for the group 1.
What do you mean?
मतलब किसी अगर हम ऐड करें ट्रांजिशन मेटल्स तो 18 हो जाएंगे.
That's fine. That's fine. So that makes aluminum in group 13. So the middle 10, we ignore them anyway. So 13 is again taken to be 3. It has 3 in the last shell. So aluminum is in group 13. So it has 3 in the last shell. So it will lose those 3. But nitrogen in group 15 or group 5. So it has 5 in the last shell. So it loses, it can either lose 5 or it can gain 3. Which one's easier? Which one takes less energy? Gaining 3, right? So that's what it does. Hamza, do you get it now?
Yes, thank you.
Great, great. Okay. How do you name a formula if it is given to you. So for example, if I told you PbCl2, can you name this substance? So Alicia, I just read your question. Do you understand it, or should I answer now? Yeah, sure. So Alicia's question is that how do we get the charges for aluminum nitride? So for that, you have to look at the group numbers. So for example, we know aluminum is in group 13, so it has 3 in the last shell. So from 3, it has to, remember, it has to go to 0 or 8. So which one's easier? From 3, it's easier to go to 0. So that's +3 because it loses 3 electrons. Similarly, nitrogen is in group 5 or 15. It has 5 in the last shell. Again, 0 or 8. 8 is closer. So nitrogen goes to 8 by gaining 3 electrons. So N is -3, Al is +3, and that's how you get these charges. Okay, let's look at this one. I want to know the name of this thing, but before I know the name, I have to know the charges. So are there any charges that I know of? I do. Remember, try to ignore these charges if you can. Chlorine is in group 17 or 7, which means it needs to gain 1. It will get -1. Now, how much total negative charge do I have? -2. To cancel it out, I will need +2 on lead. And remember, they always cancel out the charges, and that's how you figure out the charge. So now you know this one is lead 2, and this one is chloride. Now, why did I say lead 2? Why not just lead? Because it's a transition metal. Let's try one more.
So every transition metal needs to be written like that.
I'm sorry?
So every transition metal needs to be written like that.
Yeah. Every transition metal has to be written like this. So, Shanze, basically, I'm saying that you have to figure out the charges individually and then you name the charges. So, for example, I'll give you one more example. Let's say I have this thing. Now, I know calcium is in group 2, so it will be +2 here. And oxygen is in group 16, so it will be -2 here. And now I know the charges, right? So I can simply name this thing as calcium chloride. I don't need to figure out the charges separately because I know that calcium is in group 2, oxygen is in group 16. It's not transition metal, any of these. But remember, this only works for ionic compounds. If it's not ionic, so how do you know it's ionic compound? Go back to the very first discussion that we had. Ionic compounds are hard, they have high melting point, and they don't conduct as solids. So they might give you these properties of things and they might ask you, okay, tell me its name. So this is the method to figure it out because ionic compounds have ions. But what about molecular compounds? They don't have ions, right? So if they give us names of those things, for example, if they say you have NO2, how do you name this thing? Because it's molecular, all you have to do is just name everything and count it. So this one is going to be nitrogen, and there's 2 oxygens, so dioxide. Get it? So can you name
Can
this?
you do another example?
Yeah, sure. SO3. Can anybody name this?
Is it
Go on.
sulfate trioxide?
So it is sulfur trioxide. Yeah, very good. Again, sulfur because S, tri because 3, and oxide because oxygen. Okay. So that's how you.
What if it's 4 ion instead of
Tetra.
3?
So for example, if I had CCl4, then in this case it will be carbon tetra chloride. Okay. We can have like longer names. For example, if I said CH2Cl2. What would the name be in this case? Give it a try.
Carbon, hydrogen, 2.
Carbon, 2 hydrogen.
Wait a minute. Why should we say
Um,
two?
Oh,
Two.
carbon.
we mentioned-
हाइड्रोजन क्लोराइड डाइहाइड क्लोरीन सर कुछ ऐसा ही है
Try again. You're
Carbon dihydrogen,
Hmm.
dichloride.
Perfect. Very good, Maida.
Okay.
Yeah. So carbon dihydrogen, and we can also write dihydro if you want. Dichloride. Yep. So that's how you name these things. Okay. So the next chapter that we have is acids and bases. Wait a minute. Yeah, in acids and bases, we need to know how to measure things. So that's the first thing. With acids, you need to know how to measure pH, because pH is a very good indicator of whether something is acidic or basic. So how do you figure that out? How do you measure pH? There's two ways.
By the pH level.
Method one, use the universal indicator. Okay. So you dip the universal indicator paper, or you add a couple of drops to it if it's a liquid, and then match the color with chart. Because there's a chart given. Remember that we did this in class. And what's the other method? The other method is using the electronic pH meter, but it wasn't working the day we were trying to do it in class. So I don't think they'll ask you about it. We will practice using the electronic one in class after the exams.
Should we write down just one?
I'm sorry, Tayyib, there's a lot of noise on your end.
So you have to make it one dip.
Yeah.
फिर
So
बात क्या?
you add universal indicator in there. So either you have the universal indicator paper or pH paper and you dip that in there, or so for example, if I give you that, okay, tell me what's the pH of this liquid.
Sir, I have a question.
Yeah, go on.
Won't it be easier just use litmus paper?
Now here's an interesting thought. Litmus paper is not the same as universal indicator. Litmus paper can tell us whether something is acid or base, and just that. It does not tell us the pH.
So, sir, we used litmus paper. We didn't use the universal indicator.
We did the yellow one. Remember, it turned green in water and it went red in one acid and went orange in another weak acid.
Oh, okay. So should we know the types of colors and what they
No.
indicate? Okay.
You don't have to memorize them. Like, you need to know the colors for litmus paper, that it's red in acid and it's blue in base. But for universal indicator, you just need to know the method. They will give you the key, the chart, if you need to identify it.
Sir, what are all the experiments we did in class?
What do you mean?
Can you give us a list of all the experiments we did in class?
I think there were 4 or 5 main experiments that we did. There was one with enthalpy changes where we wanted to figure out how high the temperature was if you burned some fuel. Similarly, we did one with rates of reaction. There's one with chemical bonding where we were trying to see what kind of bonding something has when it conducts electricity, or does it not conduct electricity? Is it heavy? That kind of thing. There was one about, we did multiple experiments with acids, like their reactions with metal, with the bases, with carbonate, all that. Yeah. So there were a large number of experiments that we did.
Yeah, can you like
Sir, at
There
the
was a
end, can
list.
you explain titration again?
The titration, I don't think they will ask you to do titration in criterion B or C, because I haven't seen it in any of the past papers. So I would suggest that if you still want to like review it, come to the lab sometime and you can like perform it after in the next term. But I don't think it's very important when it comes to the exam.
Okay.
Yeah. Criterion D is like discussing the information that you're given, and you obviously have to come up with an educated opinion on those things. Yeah. But there are a few things in pH, in acids that I want to cover before grade 10 comes in. We'll take some time from them. Okay, so one option that you talked about is that why does pH matter? And remember, we had a discussion on this, that pH affects the environment. So there is a link to the EPA website. Okay, so just go to EPA US and there's a document on pH. So I would suggest that you go read that. Okay, so I'm posting the link here. Okay, because it's a very useful document and I would appreciate if you can all read this. Okay, to see the effects of. So just go to pH on EPA US and read up on how pH affects the environment and all that, because that's an important point that we discussed on. The
Sir,
universal
in
indicator
the-
does tell us the pH. Yeah.
In the revision test that you posted,
Mm-hmm.
in question, in the first document, question 3, 4, and 5, uh, how do they relate to the topic?
I don't have the paper with me, so just I don't know. I'll have to look at that.
Okay.
Sir,
Yeah.
do we still go through unit 1? Do we study like gas laws and stuff, or should we focus more on 2, 3, and 4?
I would suggest you focus more on the chapters that we studied this term. Yeah. Again, I'll bring you back to the acids and bases. So another important idea about acids and bases and pH is the ratio of pH. So we did this in the last class. Many of you were absent there. So you need to know that what exactly does pH tell us? So pH tells us the strength or the ratio of hydrogen ions. Okay. pH means power of hydrogen, and that's why H is capital in this. So here's the thing. If something has a pH 1, that means its hydrogen ion concentration is in the first decimal place. Sorry. If something has a pH 2, that means its hydrogen ion concentration is in the second decimal place. Again, this is just a rough idea. So you can figure out the ratio. So for example, if I said, how many more hydrogen ions are there in one solution compared to another solution, then all you have to do is look at the pH. So if something has a pH of 1 and the other has a pH of 2, just subtract them. So 2 minus 1 is 1. So it has 10 power 1 more hydrogen ions. Let me do it again. If something has a pH 1 and the other thing has a pH of, I don't know, 6, then how many more hydrogen ions are there in this one? What is 6 minus 1? 5. So this one has 10 power 5 more hydrogen ions than the other one. Another way to get to the same answer, you just divide them. So for example, in this case, pH 1 is 0.1 as the concentration of hydrogen ion, and this is 0.01, which is the concentration of hydrogen ion. So you just divide them. So 0.1 over 0.01, use a calculator, you'll get 10, which is again 10 power 1. Similarly, in this case, it will be 0.1, and this is 6 decimal place. So 0.000, 006, 001. So you divide them. So 0.1 over 0.000, 001, that gives you 10 power 5 again. So it has 100,000 more, 100,000 times hydrogen ions compared to the other one. Another question was that differentiate between strong and weak acid if they are the same concentration. Okay, so there are 3 ways to do that. One method is you check the pH, and you already know how to check the pH, right? So you take the universal indicator, you figure out the colors, you compare the colors, and then you know the pH. So that tells you which one is strong, which one's weak. Another one is use electricity. Electric conductivity or conduction, because the one that is strong, we just figured out it will have more, it will have low pH, so it will have more hydrogen ions, which means it will conduct electricity better. So for example, if you're using a bulb, it will be brighter. If you're measuring it using the current ammeter, it will show a higher value. And remember, we did this in class as well. And the third method that we have is that you can check rate of reaction. Now, rate of reaction can be measured in multiple ways. So for example, if you reacted with, let's say, calcium carbonate, so the strong acid will give faster bubbles of CO2. So there's more rapid bubbles. Not to say,
Here's number 2. So what have you written on number 2?
hello, can you guys hear me? Yeah, sorry, there was a power failure. Yeah, so the reaction is rapid with alkalis or with bases. So that's the idea. It does not mean that it gives you more bubbles. It just tells you that it gives you more bubbles in the same time. Okay, so they're faster. Overall, you get the same amount of carbon dioxide as a weak acid, as a strong acid, if you have the same moles. Okay. That was one thing. Then was, how does dilution affect the pH? Okay, so that was another important concept, that if I have a strong acid and I add water to it, does it become a weak acid?
No, the concentration just changes.
Exactly. So when concentration changes, it changes the pH, but it does not make it a weak acid. That's an important idea. So if you add water to something, it will change its pH. So for example, if I take HCl and it has a pH of 1 and I add water to it, it is possible that I'll have HCl with a pH of 2 now, because I've reduced the concentration. Okay, but it does not make it a weak acid. So then what's the difference in weak acid and a strong acid? Does anybody recall? So a weak acid, it's not a different pH level, because I just told you that you can have a strong acid with a high pH. You can just keep on adding water, it will keep on changing its pH. So the actual difference is in the way it's bonded. So all acids give proton. right? H positive, which is a proton. But strong acids give the proton right away. Weak acids give the proton slowly, or not all of them take part in that. So strong acids fully ionize. What this basically means is that strong acids will give the H positive. So for example, if I have 1,000 of these, they will give 1,000 H positive. All of them will take part in this. But weak acids don't do that. Weak acids partially ionize. So if I have 1,000 of these, maybe 100 of them will take part in the reaction and the rest of them will not. So that's the difference in strong and weak acid. It's the way they're inherently bonded. So an example of strong acid is HCl, and an example of weak acid is HCOOH. So that's an organic acid. That's a formic acid. That's, I think it's present in bee sting, if I'm not wrong, or ant sting. I don't know. So basically, if you have 1,000 of HCl molecules, they will all take part in the reaction. They'll all give you H positive. So there's a high concentration, usually, in the same volume. And in this one, there's a lower concentration in the same volume because not if you change the concentration, like if you add water, a strong acid can change its pH. So you have to be very clear that there's a thing called strong and weak acid, and there's a thing called concentration of hydrogen ion. pH is a measure of concentration. Okay. So you can have a weak acid with slightly low pH. Why? Because it had very little water probably. So you keep on adding water, the pH keeps on changing, but the nature of the acid or base does not change because of water. Clear? Okay, another important thing. What exactly is water? Like we say water is amphoteric, or another word that we use for water is amphiprotic. How do you know it's amphiprotic? So you have to look at the way water reacts with things. So here's the thing. If I add HCl to water, it becomes H3O positive and Cl minus. Now, please study this equation. HCl had an H that it has now lost. H2O had 2 hydrogens. Now it has 3 because it gained 1 hydrogen ion. So water gained hydrogen, accepted hydrogen ion. What do we call things that accept hydrogen ion? Things that accept hydrogen ions are alkalis or bases. So in this case, we can see that HCl is acid because it lost the H positive, as you can see from here to here. And water is basic because it took the hydrogen ion from here to here. You just compare it. Now, let's do the same thing, but with like if I add sodium hydroxide to water, or if I add ammonia to water, let's do that. So I take ammonia and I add that to water, and I get this thing. Now what happens here? Ammonia had 3 hydrogens and now it has 4. It has gained a hydrogen. That makes it a base. And water had 2 hydrogens and now it has just 1. It has given that away. So this is acidic. So you can see that water is acting as a base with a strong acid, but it's acting as an acid with a base. So it is amphiprotic. And you can just identify that based on the way these things are, like the equation. Okay, somebody asked about chapter 1. So from chapter 1, you need to know how to measure temperature, like you use the thermometer, how to measure mass, use the electronic balance, you how to measure volume, you look at the values in the burette or pipette and all of that. I think we have already seen that. Also how to balance equations. I think I gave you a file for that. You can look at that, but you will only be asked to simplify basic equations at this point, not very complicated ones. You can go back to your notes as well. We did a few of them in class. How do you state the numbers to balance equation? You'd simply look at the ratios. So ratios on one side and the ratio on the other side. You can just look at that. Just try to balance a few equations. I'll upload a basic worksheet as well, so you can like practice 10 or 20 of those. That should be good enough. And I'm sorry about the way files are arranged on ManageBag right now, because it's kind of like destroyed all of it. But I think all of this should be a good revision for you, like how things react. And for criterion A and B, for criterion C, how do you measure molar mass? Molar mass is something you just look it up from the periodic table. So for example, magnesium has an MR of 24. So you'll say 24 grams of magnesium is molar mass, or 1 mole of magnesium is 24 grams. So you just look it up from the periodic table.
Okay, thank you.
All right. Take care. All the best. If you have any questions, feel free to email or post on ManageBag. Okay.
Sir, I had one
Yeah, yeah.
question. Is it okay if we just revised from the book our notes and like use other videos for references? Is that enough practice?
If you're going to use videos, then I would suggest look at the videos are more useful for criterion C or criterion
Okay.
B. Look at the investigations. From the book, you don't need to do as much. I'll send you the notes and all that. Like I've tried to review all the important concepts in your syllabus today. So I can share these notes with you as well, the ones that we did here. And I'll send the recording of this video. Like, I think we have pretty much touched upon everything you were required to know. If there's still anything missing, sure, book is helpful, but not as much. It's a very difficult to read book, if you ask me.